So we're talking about drawing Lewis structures and doing Lewis structures, obviously, drawing them correctly. And remember, you want to follow the sort of steps that we talked about, which is really you want to figure out the total number of valence electrons. You want to really find a logical arrangement for how to organize the structure. Again, the least electronegative atom is typically in the center. You want to apply all the electrons after you do a single bond to the center atom to the outside ones, and put all the electrons on in pairs on the outside ones first. If you still have electrons at that point, as we talked about, that is the point where you want to then put those electrons in pairs on the central atom. The last thing you want to do is make sure that everybody has met the octet rule. And if somebody hasn't met the octet rule, as we talked about, that's really when you want to start doing double bonds or triple bonds to fix that. And to fix that, remember that we do that by, as in this example here with SO2 or even N2, we bring in a pair of electrons to make that double bond. And again, what that does is keep the total number of electrons correct. Also, hopefully, will correct any problems that you have. So we did a number of examples here in terms of drawing, so we'll just kind of continue on with that there. And remember, it's really important to sort of follow that. I think we did this guy, so we'll kind of skip through him as well. It's important to follow those sort of steps and not do it by piecework. Again, if you do it by piecework, you will find yourself probably like getting the wrong picture, too many electrons, not enough electrons. So it's a very common sort of mistake that occurs when people just kind of individually try to figure out where each of the individual electrons go. It's best to think of it as these are the total number of electrons that I have to distribute, and basically distribute them like we talked about. Another important sort of aspect of bonding is what is sometimes referred to as bond length. You do not have to memorize this chart or anything like that. But what we do see if we look at a single bond between carbon-carbon, a double bond, and a triple bond, we see that the length, which is the distance between each of the nucleuses, basically starts to decrease. Same effect here with the carbon-nitrogen, single, double, and triple bond. So essentially, every time we sort of start with a single bond, put a double bond on there, everybody gets closer, brings everybody in. Triple bond, everybody gets even closer to each other. And that's the general trend that we see. And that actually does relate to bond strength. So bond strength is obviously how strong a bond is. And what we see is basically that a triple bond is stronger than a double bond and is stronger than a single bond. It's not like a double bond, as it says there, is twice as strong as a single bond or anything like that. But that's the general trend that we see, and it has to do with really the bond length. I sort of related to like a brand new pencil or a pen, right? If you had like a pencil or a pen, nice and long, you could pretty much just take it and snap it pretty easily with probably no problem. If you take like a chemistry exam and all you have left is like an eraser and like a little small nubbin of a pencil, super hard to try to break that, right? Everything's really compact together, very strong, and it's very hard to break or snap. And sort of the same thing with the bonds. Again, the triple bond much stronger than a double or a single bond, again, because everything's really brought in close to one another, and everything's being held a lot tighter in that case. I think we've touched upon this when we were doing our Lewis structures, but just to reiterate, there are things that are known as resonance structures, and resonance structures really do sort of develop when, for lack of a better description, we have essentially more than one place where we could put the double bond. So for example, we did the SO2 earlier, it was on that previous example. And when we drew the SO2, we got to kind of, this point. And, we had electrons on, all the oxygens on the outside. And we decided perhaps that we were going to make the double bond by bringing these electrons in. But we could have just as easily brought the electrons on the other side in. And that would give us another structure, which is sort of an equivalent structure, almost like an identical, exact same type of structure. that would look something like this with the double bond over here on the right-hand side. So really a resonance structure is just when, you have more than one sort of spot where you could do that double bond. The truth about it is that those double bond electrons are sometimes referred to as being delocalized, which means, if this is the oxygen, this is the oxygen, this is the sulfur. In certain cases, the double bond electrons are over here. Other times it's moving and they're over here, which would represent the double bond on the right versus the double bond on the left. The true structure is probably somewhere in between both of those. And that's why we could draw these sort of resonance structures, usually indicated by, this sort of arrow. If you're not asked to draw a resonance structure, you absolutely would not have to draw a resonance structure ever. Any one of these three, for example, these are three carbonate structures here, and any one of these three would have been sufficient if you were asked to draw carbonate. The charges you don't have to worry about for our class, so you can just get rid of those charges. But basically, if we drew carbonate, we have the ability to put the double bond up on top, and we just as easily could have put the double bond to the left or right, which would give us pretty much an equivalent structure here. A single bonded, imagine that's a single line. And then obviously, like we see on the bottom there, we could have done it the other way as well and double bonded up over here as well. So a resonance structure is just when you can draw more than one structure, because essentially one structure doesn't really adequately describe what's going on. The benzene ring, which is sort of crossed over there, looks something like this. It's basically 3 carbons. Each of these guys are carbons, 6 carbons, sorry, and 3 double bonds. And you could draw those double bonds sort of in the other direction here. Or you could sometimes, a lot of times with benzene, you'll sometimes even see a circle drawn in there. And what that indicates is that those double bond electrons are basically moving around. And again, we'll see benzene definitely when we get into organic chemistry. And a lot of times they will be drawn sort of like that. But it basically has those 3 double bonds, which allows it to basically move from one spot to the next. So in our class, you don't probably have to worry too much about resonance structures unless you're specifically asked to draw one. I don't anticipate probably specifically asking you to draw one, so you'll probably be okay. But you should kind of know what it is and why you kind of see multiple structures. Any questions on that there? Now, we've talked about the octet rule, which is basically the idea that everybody except for hydrogen pretty much wants 8 electrons around it, and they will continue to make bonds until they get there. Hydrogen, remember, only needs 2. But there are some exceptions to the octet rule, and let me be very clear here. For our class, everybody will obey the octet rule. So everybody will obey that octet rule in our class. But again, it's something you should be aware of, that there are things that do not obey the octet rule. You will never be asked to draw anything that doesn't obey the octet rule in our class. But there are 3 major exceptions. So let's talk about those 3 major exceptions. One is an incomplete octet. There's actually things that are perfectly happy with less than 8 electrons. And the major one is really boron. So when boron's involved, a lot of times it is sort of what is known as electron deficient, and it has less than 8 electrons around it. It's a very common sort of exception. Not too much other. Beryllium, which is sort of like a metal, doesn't really kind of do this guy anyways, but he's comes out. Aluminum, which is also a metal. So usually it's boron that you see, but one thing that sort of will happen is what is known as, again, an incomplete octet, which means it has less than those 8 electrons. And again, you will not be asked to draw any of those, but that is obviously one exception. Another exception to the octet rule is what is known as an odd electron molecule. Odd electron molecule means that since we put on electrons in pairs, if you had an odd number, you will end up with one unpaired electron basically here, like an NO and NO2. Now, with one unpaired electron, these are sometimes referred to as like free radicals, like in atmospheric chemistry, chlorine chemistry, it does that a lot. They're very reactive because of that. They're not super happy about being one unpaired electron. So to try to fix that, he usually wants to react with something and it makes them very, very reactive. Now, if you ever continue on to take more chemistry, the last sort of exception to the octet rule is what is known as the expanded octet. And that's one that you see a lot in chemistry. Again, not in our class, but in a lot of other chemistry classes. That's the exception to the octet rule that you see a lot. Expanded octet means that basically it can actually go over 8 electrons. So it can have more than 8 electrons when it is in a situation. And that usually occurs on the periodic table right around where sulfur is hanging out. So if you look on the periodic table, right about there is sulfur and chlorine, and then we got phosphorus, and they're very badly drawn periodic table. We got something looking like this, but these guys, where sulfur is, it's on period number 3. And what that means is to sulfur to the left, to the right, and down, it actually has the ability to go over 8. And the reason for that is it's on the 3rd energy level. And when n is equal to 3, if you remember when we talked about electron configuration, on the 3rd energy level, there's s orbitals, there's p orbitals, and there is d orbitals there. So because these guys have d orbitals, even though they may not be using them, they actually have a place where they can kind of stash all the extra electrons. And that's where they actually end up in this case, which is in the d orbitals. What that means is if you go one period above them, things like carbon, nitrogen, oxygen, and so forth, these guys are in the 2nd energy level. They can never go over 8 because they don't have those d orbitals. So these guys have the ability to go over 8, and they could go upwards of like 12 electrons around them and be perfectly happy. So something like SF6 is kind of what it sounds like. I won't draw all the outside electrons, but basically it's got 6 fluorines attached, and this sulfur would then have 2, 4, 6, 8, 10, and 12 electrons around it. It's actually perfectly fine. Also, why when you Google structures, which you shouldn't do, but when you Google structures for something like sulfate, you will commonly see this structure pop up, which obviously is an expanded octet. But if you follow the rules for drawing sulfate, like we talked about, you actually should end up with all single bonded, obeying the octet rule. And there's a reason why there's a difference in these structures, and that reason is way beyond our class, so we don't have to worry about it here. But if you were asked to draw sulfate, you really should draw for our class this one here, obeying the octet rule. This one here is correct, doesn't obey the octet rule. So these are 3 exceptions to the octet rule. You could have an incomplete octet, which basically means you got less than 8 electrons. You could have an odd number of electrons, which means you got an unpaired electron, or you can have an expanded octet. And again, for us, you just need to know what the 3 exceptions are, but everything that you draw should obey the octet rule. I'll write that one more time. Yeah. So everything that you draw here should obey that octet rule. Any questions on those exceptions? Okay, so we're going to kind of talk here at the end about geometry and Vesper and molecular geometry. So we're going to talk about geometry, and geometry is, you can kind of use your Lewis structure to help you decide what maybe the 3-dimensional structure of the molecule would be. Remember that when we're talking about bonding, what we're talking about is electrons. And because there's electrons involved in bonding, there's obviously going to be electrons near other electrons. And that creates a problem because electrons are negatively charged. So when you get multiple electrons near each other, they're not going to be very happy because we got negative near negative. They're going to want to try to get away from each other as far as possible. They can't completely escape each other because obviously they are bonded together, but they do try to basically stretch and move and kind of bend themselves in a way that sort of maximizes to the best of their ability a way of escaping each other without obviously completely escaping each other. And what that ends up doing is giving us different structures or geometries for molecules when we talk about them. And it is, again, based on that idea of really those electrons being repulsed by each other, going from a negative electron and a negative electron near each other, and again trying to sort of get as far away from each other as possible. So that brings up the idea when we talk about geometry, which is known as Vesper, which is the valence shell electron pair repulsion model, and that is a mouthful there. And it will basically describe the electron geometry or the arrangement of the electrons. It'll also describe the overall molecular geometry. So we're going to talk about two different names here. One is what is sometimes referred to as the electron pair geometry. And electron pair geometry basically describes the three-dimensional arrangement of the electrons around the central atom. And it's always the central atom here that we're interested in. And we'll also talk about the molecular geometry. And there'll be a name for molecular geometry. It's sometimes also referred to as the shape. And that's basically the overall shape of the molecule or ion. Now, we deal with two types of categories of molecules, one that have no lone pairs on the central atom, which means when you draw the Lewis structure, no dots on the central atom, and ones that do have lone pairs on the central atom, which means when you draw the dots, when you draw the Lewis structure, you have dots on the central atom. Now, there's one really sort of very important rule when you're doing geometry, and it really is this rule right here. When you're doing geometry, and you draw a Lewis structure that has either a double bond or a triple bond, when you are counting things, those count as one electron pair and also one bond. So if you draw a double bond or triple bond in your Lewis structure, it will essentially count as only one electron pair when you're counting them and one bond. And again, we only do this with geometry. We do this sort of counting, and that's a very, very important rule. The last one, not so much for us, but again, you could draw a resonance structure, and you really can apply geometry the same way to everybody, and it will work out the same basically, regardless of your resonance structure. You'll usually end up with the same structure. So let us start with really the simplest molecules of all. And there's a lot of like X equals this and that type of stuff. You could kind of ignore a lot of this, but basically the simplest molecules we could have are diatomic molecules, which means that there basically are only two atoms involved. So something like H2, something like F2. Doesn't have to be the same elements, something like HF, something like HCl. These are all diatomic molecules, and essentially when you only have two atoms that are these diatomic molecules, the geometry is always linear. You don't have to even think about it. The geometry will always be linear. There's basically only way to arrange two things, right? Shortest distance between 2 points is a straight line. So it will always be a linear geometry. Again, no matter if it's two of the same thing, no matter if it's two different elements, no matter if there's a double bond, no matter if there's a triple bond, as long as you see two, that is your answer for geometry. It's always going to be linear of each other, basically a straight line, kind of 180 degrees apart from each other, if you want to think about that. But there's not really three atoms to make an angle like that. So it's basically just as kind of a straight line. Now, when we get into guys that have three or more atoms, there's a couple of things we need to consider. So let's take a look at this example here. And when we're doing geometry, again, there's these two names, electron pair geometry and molecular geometry. And what you want to do is always go to the center atom and basically count up what you got going on. We have one electron pair there, two electron pairs there. So we have two electron pairs. And number of bonds, we have one bond there and one bond there. That is 2 bonds. So something with 2 electron pairs, its electron pair geometry name is also going to be linear in this case. Something with 2 electron pairs and 2 bonds, the molecular geometry name will also be linear in this case. So when you look at your Lewis structure, if you end up with 2 electron pairs on the central atom and 2 bonds only, no dots, nothing there, going to end up with linear for the electron pair geometry and linear for the molecular geometry. As you can see in this picture, basically they end up being 180 degrees apart. What's essentially happening is these electrons here and these electrons here decide we're going to go as far away from each other as possible. They end up basically on opposite ends of a straight line. Any questions on that geometry there? Then let's look at one where we have a central atom and 3 things attached to it. Now, again, if we look at our electron geometry, our molecular geometry, I'll just abbreviate it there. Again, we want to look at the central atom. It has 1 electron pair, 2 electron pairs, 3 electron pairs. Always the central atom is where you want to look. Now, how many bonds does it have? It has 1 bond there, 2 bonds there, and 3 bonds there. So something with 3 electron pairs in terms of the electron pair geometry will be known as trigonal planar. And that is because, as you can kind of see, it makes like a triangle here, which is why it's sometimes called triangular because of that. Something with 3 electron pairs and 3 bonds has a molecular geometry of also trigonal planar. Same thing sort of happens here. We get a bond angle of 120 degrees. This electrons here try to escape as much as they can. The difference is we got a 3rd electron pair here. So again, what they end up trying to do is separate out at the corners of a triangle and basically get as far away from each other as possible. So 3 electron pairs, 3 bonds, trigonal planar for both the electron pair geometry and also the molecular geometry. Any questions on that there? They're actually the same. So some people will call it triangular for both. You can actually use it for both. But most people call it trigonal planar. And that's really what most people call it. But some people still occasionally call it triangular because, again, it kind of makes a triangle sort of appearance and stuff like that. So they're basically the same sort of description. It's just kind of like a, I don't want to say older name and newer name sort of deal, but that's sort of how some people sometimes refer to trigonal planar as either triangular or trigonal planar. Again, most people nowadays kind of go with the trigonal planar sort of naming of it. Other questions on that? Then let's continue on and look at the next example, which apparently got really messed up there. So I'm just going to redraw that correctly for you. So looks something like this here. All right. So if we do kind of same thing, electron pair geometry and molecular geometry here, again, we're going to look at the central atom. It's got 1, 2, 3, and 4 electron pairs. Also has 1, 2, 3, and 4 bonds. Something with 4 electron pairs in terms of electron pair geometry is what is known as tetrahedral. Tetrahedron, if you're old like me. Something with 4 electron pairs and 4 bonds also will have a molecular geometry name of tetrahedral as well. Has a bond angle of 109.5. Here again, we have now 4 bonds, so they can only kind of stretch out again as far as they could get. There's all these extra bonds in the way. So obviously as one thing moves, the other bonds move with it. And if you put more bonds and stuff in there, you know, it kind of limits how far they can kind of move away from each other. So 4 electron pairs and 4 bonds are what are referred to as tetrahedral for both the electron pair geometry and the molecular geometry. If you look at all the structures we just did in terms of geometry, they all share in common no lone pairs on the central atom. What that means, if you look at all these pictures, no dots there, no dots on this guy, and no dots on the central atom of this guy. And what we see in terms of the names, the electron pair geometry name and the molecular geometry name, they're exactly the same. So if you draw a Lewis structure and you have no dots on the central atom, both the electron pair geometry name and the molecular geometry name should be the exact same name. And the reason for that is all the electrons that are present are the exact same type of electrons around the central atom. They are all bonding electrons. So you got bonding electrons near bonding electrons. And for the most part, that is like the best situation for bonding. Those electrons can almost tolerate each other, so they don't try to go as far as possible. When we get into molecules or structures where we do have non-bonding electrons on the central atom, what that ends up doing is creating a lot of different interactions based on the types of electrons that are present. We could get some bonding and bonding electrons, which is kind of the best situation. We could get some non-bonding electrons and bonding. So these are like dots near lines. These are all lines, no dots. And that's middle road. Worst situation is when you get dots near dots, non-bonding electrons near non-bonding electrons. They super do not want to be near each other. They try to run as far away as possible. So when we introduce these non-bonding electrons on the central atom, what we end up getting is, A, there's not an extra bond there. There's now just dots and non-bonding electrons, and they don't want to be near each other. So they can now stretch out a little bit further, and we end up getting some different geometries. So the one name that actually changes is the molecular geometry name. The electron geometry name stays the same. Is based on the number of electron pairs, but the molecular geometry name will change in this case. So when you draw your Lewis structures and you see those non-bonding electrons, they're going to change the molecular geometry name, but the electron pair geometry name will still be the same because there's still the same number of electron pairs around the central atom. Let's take a look at the first example here. This is SO2, which we did draw earlier. So it looks like this. I'll do the double bond over there. Now, when we look at the central atom and we do our electron pair geometry and our molecular geometry, I look at this central atom. I have one electron pair here. I have one electron pair here. Doesn't matter if they're dots or lines when you're counting. And now I have a double bond. Remember that a double bond will only count as one electron pair. So for this molecule, I actually only have 3 electron pairs in terms of the geometry. And in terms of bond, what do I have? Well, I got one bond here. Again, the double bond only counts as a one bond as well, double or triple. So I basically have 2 bonds. Now, something with 3 electron pairs doesn't change. It's still known as trigonal planar for our electron pair geometry. But now I have bonding electrons near bonding electrons. I have non-bonding electrons near bonding electrons. And there's not an actual bond here where those dots are. So these guys are going to be able to kind of spread out and move away from each other. And we end up with a geometry known as angular, or sometimes people will call it bent angular. Has a bond angle of just under 120 degrees. So it looks kind of like this sort of angular bent type of shape. And again, it's got a bond angle just less than 120 degrees. So 3 electron pairs, but only 2 bonds. Electron pair geometry, trigonal planar, just like it was before for 3. But the molecular shape is angular or bent angular. Any questions on that one? Now let's take a look at another one that's got some non-bonding electrons happening there. This is geometry. Central atom, here's the nitrogen. We got 1 electron pair there, 2, 3, and 4 electron pairs. We have 1 bond, 2 bonds, and 3 bonds. Something with 4 electron pairs, just like we saw earlier, is tetrahedral. But now again, we got this same situation. We got bonding electrons near bonding electrons. We have non-bonding electrons near bonding electrons. So the geometry that it ends up getting is something that is known as trigonal pyramid. And this is what it kind of looks like. Again, those bonding electrons kind of go away from the non-bonding electrons, kind of makes this pyramidal shape on the bottom. And with those non-bonding electrons up on top, a triangle type shape as well. So that's what trigonal pyramid sort of looks like. Let us take a moment here to talk about a name or 2 names that's really important, not to, kind of just not do it correctly. That is trigonal pyramid. There is a difference between trigonal pyramid and trigonal planar. Trigonal planar is 3 electron pairs and 3 bonds. So if you mean trigonal planar, you should write trigonal planar. If you mean trigonal pyramid, you should write trigonal pyramid. You should not just write trigonal and let me choose, because I probably will choose wrong. Nor should you do my other favorite one. It is definitely trigonal. That is, of course, pyramid. I just wrote there. I mean, planar. It was planar. It's one of those. So make sure that you can clearly see it, or I could clearly see it, and you make your choice. Again, if you make me make the choice, you will get one of those. If you write something like that, you will get one of those. So make sure that you do choose it. Again, there is a difference between those two in terms of what they mean. Again, trigonal planar being 3 electron pairs, 3 bonds, and trigonal pyramid being 4 electron pairs and 3 bonds. Any questions on that difference there? The last geometry that we deal with in this class, and there's obviously a lot more that we don't deal with, but the last one here is something like water. And again, if we look at the electron pair geometry and the molecular geometry here, central atom, again, has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. It has, in terms of bonds, 1 bond and 2 bonds. So something with 4 electron pairs, just like the last few, is going to be tetrahedral. Now, because it has 4 electron pairs, it actually has all the worst interactions happening. It has bonding electrons near bonding, which is not too bad. It has non-bonding electrons near bonding electrons, worse, but it has non-bonding electrons near non-bonding electrons, and those two do not want to be near each other. So what ends up happening is those non-bonding electrons kind of go this way, and as they go that way, the bonding guys kind of come down, and it creates a shape which is known as bent or V-shaped, which is why when you see water drawn, it's usually drawn like this, like a V, right? Kind of bent or upside down V type of shape. And again, that's really because those non-bonding electrons near those non-bonding electrons definitely do not want to be near each other. Any questions on that? So those are the geometries that you need to know. Again, you need to know the electron pair geometry. You need to know the molecular geometry. You do not have to worry about bond angle for our class. But again, if you draw the Lewis structure and everybody is no dots on the central atom, both names will be the same. If you draw the Lewis structure and you see dots on the central atom, the molecular geometry name is the one that changes. So if we just kind of look at a few other examples of some stuff that we drew earlier, here is our nitrogen. This guy would be linear, as it's just 2 of them together. We saw carbonate earlier. Looks something like this. Carbonate has 1 electron pair, 2 electron pairs, and again here the double bond only counts as 1, so that's 3 electron pairs. Has 1 bond here, 2 bonds here, and again this double bond only counts for the purpose of geometry as 1. That is 3 electron pairs, our bonds. 3 bonds and that hour of sleep. 3 bonds and 3 electron pairs here. That is going to mean that the electron pair geometry is going to be trigonal planar. And the molecular geometry will also be the same name. And again, I know it's the same name because there are no dots on the central atom. So again, they're going to be the same. We also, I think, drew this guy as well. This guy will have the same geometry as water, basically. It has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. And it has 1 and 2 bonds, which means just like water, the electron pair geometry is tetrahedral because there's 4 electron pairs. But because there's only 2 bonds, the molecular geometry here would be bent or V-shaped. Any questions on that there?
I have a question, Professor.
Yeah.
So would we draw it, if you asked us to draw water, would we draw it at like the top with the 2 lone pairs, 1 on the top and 1 on the bottom, or would we draw it like the bottom example, like off to the sides?
So for me, if I asked you to draw a Lewis structure, you don't need to draw it with the geometry if that's sort of what you're asking. You could just kind of draw straight like the top one is perfectly fine. Unless you came across a specific question that asked you to do that, but I probably wouldn't ask you to do that. So you don't have to, when you draw Lewis structures for me, sort of draw it with the geometry for us. Yeah.
Great. Thank you.
You're welcome. No, you could either write bent or V-shaped is fine. And that's why the earlier one with the SO2, I use angular. Some people do use bent angular, and there is a difference between this bent shape, if you will, and the one that we saw with the SO2. There is a difference between these two. So for us for here, you should use something like angular or bent angular for this one, and either one would be fine. But you really shouldn't just use V-shape for this one because it's really not V-shaped, because the bond angle is actually different for this, say this guy here, than say the one with water at the end. So there is sort of a difference between those two. And to answer probably your direct question, if you had water and you wrote bent, it would be fine for the geometry, molecular geometry. If you wrote V-shaped, it would be fine for the molecular geometry as well. Other questions on that? Okay, then let's finish up talking about this sort of chapter here. And the last thing we're going to talk about is really polarity. So this is a table similar to one that you have in your book of the different shapes and stuff like that. So you should have one very similar to this table. So earlier we talked about sort of bond polarity, and what we're going to talk about here is the entire molecular polarity. So bond polarity is when we talk about an individual bond between 2 atoms. And that's where we use electronegativity. So if you remember, we did some of those difference in electronegativity values, and that helps us with our bond polarity. Now, bond polarity and molecular polarity are different, but they are the same result in one type of molecule, which means if you have a diatomic molecule, which again means there's no central atom, there's only 2 atoms. And so, for example, if I had something like fluorine, and I won't draw the electrons, but if you remember, the difference in electronegativity here would be 0, which means that this is a nonpolar bond. And because this bond right here is nonpolar, it also happens to be the only bond in the entire molecule, which means that this molecule would also be nonpolar. And what that means is, as a whole, this entire molecule is basically sharing electrons equally. There's no like negative side or positive side to that molecule. It's like a perfect kind of distribution of electrons. It's kind of neutral if you want to think about it that way. If we had something like HF, for example, if you remember, if we looked at the difference in electronegativity, the fluorine is more electronegative, so we could draw that arrow where it points to the more negative side, and this is the more positive side. Now, this guy has a polar bond because of the difference in electronegativity, but for the same reason as below, because this is the only bond in this guy, it would also be considered a polar molecule because of that. So diatomic molecules are really easy to determine. Is the molecule itself polar or nonpolar? And it's because they only have one bond. So if you're able to identify the bond as being polar or nonpolar, you will be able to identify the molecule as being polar or nonpolar because only one bond makes up the whole thing. A polar molecule means that, this side of the molecule is more negative where the fluorine is, and this side is more positive. Now, when you're dealing with more than two atoms, three or more atoms, you have to look at two things. You have to look at, are there polar bonds? And you have to look at the molecular geometry. So, for example, if we looked at carbon dioxide, which looks like this, and again, I won't draw all the electrons on the outside. The bond between carbon and oxygen is polar. They're in the same period on the periodic table. Oxygen is more electronegative. So we could draw those arrows heading towards the oxygen. This guy has polar bonds. So it would make sense to you probably to go, it has polar bonds. This probably should be a polar molecule. But we have to look at the geometry here. And this guy has one electron pair, two electron pairs, and two bonds. So something with two electron pairs and two bonds is going to be linear. It's 180 degrees from each other. And what that means is we basically in this situation have oxygen pulling this way, but we have oxygen also pulling this way. And I'm actually pulling really hard on my pen here, and it's not going anywhere. So although they do have polar bonds, because of the geometry of CO2, they actually cancel each other out. And this is actually a non-polar molecule because of that. And that's because these little arrows that we draw are known as vectors. They have direction, they have magnitude. And in certain cases, they cancel each other out when they're equal and opposite of each other. And in certain cases, they will add to one another if they're kind of heading in the same direction. And that's different than when we look at water, which is what we were looking at just a minute ago. We had water, and we'll draw it with the geometry so we can kind of see what's going on. Between oxygen and hydrogen, oxygen is more electronegative, so it's heading this way, and it's heading this way. And so water does have polar bonds. The geometry of water is, as we talked about, 4 electron pairs and 2 bonds, which is bent or V-shaped, which is why it's heading that way. So you could kind of imagine everybody going towards the top, and everybody kind of pulling from the top. It's going to kind of move. And there's a net, what is known as a dipole moment heading in, if I can see where I'm drawing here, maybe. Where'd it go? There it is. Heading in this direction, a net dipole moment where the oxygen part of water is more negative, hydrogen part is more positive. And the reason for that is these vectors, which again, you can kind of draw the vectors if you really want. But if you kind of think about it, we have the oxygen hydrogen vector, coming this way. We also have, draw it this way, I guess. We'll go that way. We have the hydrogen oxygen vector going this way. We have the other one sort of adding to it going in this direction, and it has a net movement heading upwards in this case. And that's a lot of drawing and stuff like that, and nobody wants to do any of that type of stuff. So there must be a more simple way to figure these things out, and there really is. So the very simple way to sort of figure these out is if you follow these general rules, you'll usually be okay. There are certain symmetrical geometries. And these are things like trigonal planar, and we're talking about molecular geometries here, and tetrahedral. And what these guys have in common is if you draw that central atom, there's no lone pairs on the central atom, Ca, central atom. And if you have this situation and everything on the outside is the same atom, it will be nonpolar. They will all cancel each other out. It will become a nonpolar molecule. So what does that mean? So if I take something like this, carbon with some fluorines, and again, I won't draw all the electrons. When I look at this central atom, I do not see no dots. I see everything on the outside is exactly the same, which means this guy's going to be nonpolar. Again, because they're going to pull equal and opposite of each other. And that's sometimes how we think about sort of polarity. It's like tug of war, pulling. So if people are pulling equally, nothing's going to happen. You know, if somebody pulls a little harder, things are going to move. And that's sort of how we do that. Now, if we have this same guy, but we swap out one of the fluorines for a hydrogen, what's going to happen now is the carbon is going to go towards the fluorine there. That guy's going to go towards the fluorine. He's going to go towards the fluorine. But between carbon and hydrogen, it's non-polar. So there's going to be kind of no movement. So these three guys are kind of pulling this way. This guy at best is actually going with them a little bit. So you could kind of imagine this whole thing is going to move. And we will then go from a non-polar molecule to a polar molecule. So no dots on the central atom. Everything on the outside is the same. Pretty safe bet to write it's a non-polar molecule. No dots on the central atom, but everything on the outside is not the same. Probably a safe bet to call it a polar molecule. Now there's some unsymmetrical geometries.
I'm sorry, Professor, could you repeat that one more time?
Yeah. So if you draw a Lewis structure and you have no dots on the central atom and every single element on the outside is the same element, it is a safe bet to write it's going to be a nonpolar molecule. If you have a Lewis structure where you have no dots on the central atom, but everything on the outside is not the same element, like in this situation, it probably will be a polar molecule in that case. Other questions on that?
Thank you.
You're welcome. Now, if we look at unsymmetrical geometries, these are things like our bent, our V-shaped. These are things like our trigonal pyramid. These are things like our angular. What do these guys have in common? Well, these guys have in common the fact that there are dots on the central atom. And if you draw one of these guys and there's dots on the central atom and everything on the outside is the same atom or element, it will most likely be a polar molecule. So let's take a look at like our water, right, that we had before on this previous page here. When I look at water, over here, I look at the central atom, I see dots, I see same element, I see polar molecule because of that. I look at my SO2 that we drew earlier. I see dots, I see same elements, I see polar molecule. And it really is almost that simple. Yes, don't overthink it. You probably can figure it out very easily, sort of doing that. So let's take a look and we see if we could apply that to what we see on the bottom here. Forget all the arrows and stuff. We look at the central atom, no dots, but everything on the outside is different, polar. Yeah, it's just like this example. We look at the central atom, no dots, everything on the outside is the same, like here, non-polar. We look at the central atom, I see dots, I see everything on the outside is the same, polar, like this guy. I look at the central atom, I see no dots, but everything on the outside is not the same, icy polar molecule. So that's a very quick way, and probably 97, 98% of the time, you'll be okay. It's a very good way to sort of figure out the polarity. Any questions on molecular polarity? The only one really that you have to really concern yourself with is linear. Like in the case of CO2, they could be going opposite and cancel each other out, but they could all be heading in the same direction if they're linear. So that's really the only one you kind of have to think about it. But again, it's sort of a straight line. You could kind of do the tug of war approach. If somebody's pulling more one way, it's going to be polar. If they're pulling equal or opposite, it's going to be nonpolar. If they're kind of heading directly at each other, it will be nonpolar as well. So, those are ways that you can kind of think about it. And that should wrap chapter 6, I think. Any questions on any of that stuff there?